Thanks for the introduction. So this is a joint work with Amedeo, Cesta, and Andrea Orlandini from the CNR, the National Research Council of Italy. So briefly, just to introduce, I will give you a short research context of this work, that is the cyber physical systems so the industry 4.0, that they aims at enhancing the productive entities, a modern production system by pushing an ever tighter interaction between artificial communication and physical processes within the factory. And so this trend aims at transforming the current production system towards a so-called anthropocentric scenarios, where basically the human workers and machines, that maybe artificial robots or computational machines, so work together and have some benefits from this collaboration. So in some way combine human skills with robot and other intelligent entities that can be found into a production system. And in particular, for what concerns a particular field of this area, that is the human-robot collaboration, the goal is to achieve a symbiosis between the worker and the intelligent robots that together collaborate in order to achieve and to push a common shared production objectives. And this continuous interaction between the human and the robot raises several challenges with respect to the technologies, and in particular to the autonomy of the robot, but also the safety of the human operator. And so this is mainly because the human behavior that collaborates with the robot is not predictable or controllable from the perspective of the controllers, so from the perspective of the technologies that control the robot. And so the robots should be endowed with some kind of cognitive capabilities that allow the robot and the controller to know the production environment, to know which are the goals that should be achieved, and understand what's going on into the production environment. So understand events and also situations that can be observed into the environment, and so automatically and autonomously adapt its behavior in order to better support the human operator and the whole production process. So our objective in this area is to push the integration of artificial intelligence and robotics technologies to realize these cognitive capabilities and move towards a kind of cognitive robot control. And for example, we have recently made some work in integrating dynamic task planning and motion planning in order to enhance the flexibility of collaborative robots when interacting with humans. And so dealing with the uncontrollability that the human worker introduce into the system. But more in general, what we want to achieve is a kind of perceived reason act paradigm that put in the center the semantic technologies that should be used, integrated with other artificial intelligence technologies, like, for example, planning and execution technologies, that basically realize the key element, and so the key functionalities that are needed to allow a robot to know what is going on, and to know the features of the collaborative process, and to know how it can support dynamically the collaborative process, and in this sense, dynamically, for example, configure the planning module, the planning technologies in order to synthesize collaborative plans that are dynamically adapted to the current situation and to the specific needs of the production environment. In this sense, the contribution of this work are to refine an ontology for human-robot collaboration that we have introduced recently, we have defined recently, and by integrating by describing through ontology design patterns the possible collaboration dynamics that may occur between human and robot when performing collaborative tasks, and then propose a methodology to support the knowledge definition, in particular with the aim of providing a process that allows, for example, in production engineering, or so more in general domain expert of a production scenarios, with a methodology that allow him to build the knowledge base, and so build an instance of the ontology in order that completely describe the production scenarios, and then use this knowledge to dynamically configure the planning and execution process in order to synthesize automatically collaborative plans that fit the actual need of the considered production process. So in this way, we can say that we want to abstract from, for example, the syntactic features that may have different planning formalism, and use semantics technologies to generalize the problem of planning and controlling the robot and synthesize automatically planning models for collaborative robots. So here is a brief description of the ontology that we have defined, and which relies on three main blocks that are the Dolce, that is the foundational layer of the ontology, and then the SSN and the Cora ontology that are some standard ontological models that have been defined for representing sensory data and representing autonomous robots or in automation. And in particular, the idea is to define this ontology following a context-based approach and structure the ontology and the concept of the properties that we have defined in a number of contexts that describe the production process from a specific perspective and some synergetic point of views. In particular, we can see here the three main contexts that we have defined, that are the environment, the behavior, and the production, that describes the production process, as I said, from different perspectives, as we will see in the next slides. And this is to support a flexible representation of the scenario, and in particular that is focused mainly in characterizing the functions that the agents, like for example the human worker or the collaborative robots, can perform according to their capabilities, to contextualize these capabilities with respect to the production needs, and so with respect to the production process and the operational constraints that should be satisfied in order to correctly carry out the objective of the collaborative scenario. So this ontology has been extended by introducing, as I said, the concept that and the properties that were needed to define some recurrent situations or recurrent dynamics of collaborative process, and in particular to characterize how, in general, human and robot work together in these kind of scenarios. And according to the literature, there are 4 types of collaboration that have been that are typical, that are recurrent in these kind of scenarios, and we have defined some kind of ontology design pattern to facilitate the representation, to provide a well-structured way of representing these instances of collaboration into the knowledge base, and then, as we would see, to facilitate the knowledge definition process. So in general, we have these 4 types that are the independent collaboration, where the human and the robot work independently on different tasks, but share the same environment, and so the same workspace, physical workspace. Then we have the simultaneous scenario, where the human and the robot simultaneously perform different tasks on the same object, or perform the same different operations on the same objects, but they are not required to be strictly synchronized in this sense. They just have to perform some operation on the workpiece. Then we have the sequential collaboration modalities, where the human operator perform different operations on a workpiece, and they are subject to some temporal constraints, so present constraints. So, for example, the operation of the operator can start only after the robot has ended its operation. And then we have the last collaboration modality, that is the supportive, where the human and the robot are strictly constrained to work in parallel. So in this case, the human and the robot are basically performing the same type of operation, so the same operation on the same workpiece at the same time. So this is the more strict dynamics that are useful, that are usually used in collaborative scenario. So at this point, once we have defined ontology and the information that the domain ontology that characterize the information and the knowledge that is typical in a production scenario, the definition of an instance of this knowledge that completely characterize a specific instance of human-robot collaboration scenario is not easy to define. And in this regard, we have designed a modeling methodology that aims at proposing a well-defined structure to how to define the concept, the instances of the elements that are relevant to completely characterize a production knowledge, and to integrate, when possible, also knowledge reasoning mechanism that can support the definition of this process by, for example, anticipating some possible choices or instantiating some knowledge when possible according to the input data from the user. So facilitate the domain expert in the definition of the complete knowledge. So this is the pipeline of the modeling process that we have designed. Now we have in the paper we have described the theoretical, so the general approach that we have envisaged and that we have implemented manually, but in parallel we are working on integrating this structure and the structure of the ontology model that we have defined into a knowledge engineering tool and we have presented some initial result at the conference Roman this year, where we have defined a graphical knowledge engineering tool that can be used by domain experts that are not familiar neither with planning, neither with ontological and knowledge-based reasoning, to define the characteristics and the knowledge of their production scenario. And just to give some more detail about the level that we have envisaged in this process, we use basically the structure of the ontology and the structure of the context that we have defined in order to incrementally build a knowledge that completely describes the production scenario. So we start from the lowest level of abstraction, that is the environment level knowledge, where the domain expert is supposed to define to describe the physical layout of the environment, of the production environment, so the devices that are part of the environment, the objects, and the robots, robotic devices that will be part of the production process. And to define these instances, we strongly rely on the two ontology, the SSN ontology and the core ontology. The SSN ontology, that is the semantic sensor network ontology, is a standard ontology defined to characterize sensing devices that can be deployed into some physical environment, and is in particular useful to characterize the physical properties that can be, and the observation that can be produced by these sensors in order to contextualize the information that can be produced by the sensor that are deployed into the collaborative cell in this case. While the core ontology is a standard defined for describing the robots, so the robotic devices, the part that can be made, that can compose a collaborative robot in this case, and also for example, the autonomy level and other information that are useful to characterize, in particular, the capabilities of the robot in terms of the general operation that can perform inside the environment, like, for example, pick objects, move inside the environment, place objects, and use some tools, and so on. And in addition to this information, we also integrate knowledge about the tools and the resources that are relevant with respect to the production objective of the scenario. Then, when we have this information, it is necessary to characterize the behavior of the agent that are part of this environment, that are the worker and the collaborative robot. And in this regard, the domain expert first specifically describe which are for example, the characteristics of the robot that are deployed into the environment, and so the embodiment of this robot that determines so the capabilities that as an agent is capable to support, and also the characteristics of the worker, because, for example, we can have worker with different skills and different so abilities and different ways to contribute to the collaborative process. And then this knowledge is then elaborated with knowledge reasoning mechanism in order to automatically infer the instances of functions that the human worker and the robot can perform according to their capabilities and according to the structure of the environment. And to do so, we in particular integrate the so-called taxonomy of functions introduced in a paper by Borgo in 2009 that generally described a a taxonomy of general functions that can be performed in manufacturing environment, but in particular focusing on the effects that these functions have on the object of the environment. So leveraging this taxonomical representation and the ontological definition of this function, we are able to contextualize the capabilities of the human worker and the robot according to the objects that are part of the environment, and automatically infer with this kind of rule, this rule on the left, automatically infer which are the actual instances of functions that a human and a robot can perform into the environment. So at this point, then we propose to define the production level knowledge, that is the knowledge that characterizes the production requirements of the environment, so allows the expert to describe the production process that should be performed, and in particular to following a hierarchical decomposition of the process. And so in this case, a domain expert can describe the process, so the production goal that should be achieved, and the methods as different types of hierarchical decomposition that can be considered to implement and to achieve the associated production goal. And so each method is composed by a number of production tasks that can be either conjunctive or disjunctive, in order to define all the possible ways in which a complex task can be decomposed into increasingly simpler production tasks, until we define some simple tasks that represent the leaves of the hierarchical decomposition that are then directly linked to the functions that the human operator and the robot can actually support. And these simple tasks are those that actually represent the primitive production operations that that require the collaboration between the human and the robot. And so in this regard, the last step of the methodology is the task contextualization, where these simple tasks are linked to the functions of the human operator, and to do so, we use, as I said previously, the defined ontological patterns of collaborative tasks in order to facilitate the definition of these tasks and the complete definition of the production process.
Alessandro, sorry,
yes.
You have only 10 minutes if you can resume.
Okay.
Go faster. Thank you. We are.
Yes. I will finish shortly. Yes.
Thank you.
So just to go straight to the end. So the key point is that this knowledge represents a kind of standard planning knowledge of the human-robot collaboration, and that can be used to synthesize a planning model for the definition of collaborative plans and collaborative process. To do so, we use timeline-based planning that has been defined in the early 90s and that has been already used in human-robot collaboration and support the synthesis of collaborative behaviors of the human and the robot. And here is just a brief description of the modeling procedure or the extraction procedure that we have defined to extract knowledge from the information from the knowledge and build the timeline-based model. In particular, we have a first step where we define the state variables that describe the general behavior of the production process and the general behavior of the human and the robot in terms of functions that they can perform. And we, in particular, define the hierarchical task decomposition through a number of different state variables that characterize the production process at different hierarchical levels. This process then, these hierarchical tasks are then linked, these state variables, so the task of the production process that have been defined into the state variables are correlated through synchronization rules that actually represent the decomposition of complex tasks in increasingly simple tasks. And then we have the last step of the procedure where we create the synchronization rule by describing also the temporal constraints that are necessary for the collaborative dynamics that are required to implement the simple task of the production process. So according to the ontological pattern that have been defined. And so we have made some experimentation to test this procedure and the overall definition, process definition of the knowledge. these are some details on how it has been implemented in ROS, and this is something that we have done within the European project ShareWork. And to do so, and to evaluate the capability of the methodology and the approach, we have considered several human-robot collaboration scenarios that are taken from the pilots of the project. In general, the different process that we have, the different scenarios that we have considered are characterized by different characteristics in terms of collaboration modalities and also in terms of complexity of the production processes. So this leads to different sides of planning models that have been defined, so different number of state variables, synchronization rules and constraints that have been defined. But in our case, in general, we can see that the times, the model generation time that has been observed in these cases is reasonable with respect to the deployment of these technologies in the real world, also because this is generally an initial cost that you pay for the configuration of the planning model, and it is not necessary to generate everything from scratch to generate different planning collaborative plans. And so that's all. This is just some image that describes some of the scenarios that we have in particular introduced with respect to the paper that has been accepted to the workshop. Just to give some input about this, in this case, the scenario was to a production line that built some trains, and the production process focused on the assembly of the windows of the trains. And as you can see in this picture on the right in the middle, the scenario is supposed that is structured in a way that there is a human operator that work around the parts of the windows that should be assembled, and a collaborative robot that is put in the center, and they perform some operations that should be synchronized in order to satisfy the operational requirements. And here is another scenarios that we have considered, but I think that I should go straight to the end of the presentation. But in general, the structure of the collaboration is somehow similar. And so, just to conclude, this work, as we have seen how we have used ontology to characterize the production knowledge that is necessary to support flexible human-robot collaboration, and in particular how the ontology and the modeling process can be used, and the knowledge extraction procedure can be used to abstract planning features, and the planning formalism used to actually coordinate the human and the robot within the scenario. And future work will focus on the refinement of the tenant tool that I cited before to better integrate the ontology that we have defined, and so complete design a more interactive engineering tool for the definition of knowledge process, and also extend the ontology to better characterize the human factor, and in particular support a better personalization of the collaboration by taking into account, for example, profiles of the worker and other useful information. So that's all for my presentation, and if you have questions, I will be glad to answer to them. So thanks.